Alrighty, so chapter 5 is probability. You'll notice it says 5.1 and 5.6. The course is having us skip a lot of chapter 5, which I think is a shame because the other parts of chapter 5 are some of my favorite things in math, but apparently it's out of the scope of this class. If you ever want to know about those things, please ask me, and then you will wish you would never ask me because I will talk your ear off about this probability. That's the problem with asking math people a question. They will answer you and you wish they hadn't, but that's okay. But anyway, going. So 5.1 is probability rules. So what things do we need to know about probability to see how it works? So I will warn you, there's some more vocab in this section that I'm just going to kind of skip over because you can read those. But the pieces we need for the formulas and such and the rules, I'll go over. So the first thing is, what is probability? And I will probably not write out that whole word ever again. For us, it'll be prob after this. This is the measure of the likelihood of a random phenomenon, which is a fun word, or chance behavior occurring by random. There is, okay, by random. So what's the likelihood this thing happens? Um, so some common things we deal with probability, it would be like dice, cards, coin flips, lotteries. So if you think of our random or our typical six-sided die, the die has six sides and the probability is the same. If we get any of the six, we roll it and any different value comes up. So what's the likelihood we roll a six? What's the likelihood we roll a two, etc.? That's our probability. How likely is something to happen? We deal with experiments, sort of. Plus, an experiment is something that's repeatable. Right? So an example would be rolling our pair of dice. So take two dice, roll them a bunch of times. We're running experiments the whole time. We can repeat this thing. The probabilities don't change of particular things happening. So we just repeat that. And that looks terrible on the big screen. Let's try again. That's good. Okay. Now I've used a word in this that we're going to define in a sec. We also have a sample space. And we're going to call this S. This is all of our possible outcomes. So let's stick with the die example because that's a really easy one to deal with. If we roll a 6-sided die, let's see if I can draw one of these. Bad, that's okay. For a single one of these, our sample space is every possible face. So we have 1, 2, 3, 4, 6. So all of our possible outcomes. We want to list everything if it's feasible. Sometimes it's not feasible. So you just kind of describe the sample space, but we're going to want to know how many things are in there. So how we say that is n of s. This is the number of objects in our sample space. So for the one above, our n of s is 6. We have 6 things in our sample space. 1, 2, 3, 4, 5, 6. Then we have events. And we typically use the letter E. That is very messy. Let's try again. And a lot of times we'll have a sub number with it. I'm going to use the letter I for now, just because we may have multiple events on the same sample space. So instead of coming up with new letters, we'll just say E sub 1, E sub 2, etc. This is one or more outcomes of an experiment. I say one or more because sometimes we could just say the probability of rolling or how many ways can we roll a 2? Or we may say how many ways can we roll a 4 or more? Something like that. So I already did that. E1. So if we're dealing with our sample space above, the 6-sided die, and our first event is an even number. So how many ways can we do that? Let's just list them. Well, we can roll a 2, a 4, or a 6. So the number in that sample space is 3. We also have to be really careful reading these. So if our E2 is roll a number larger than 4, that doesn't include 4 because 4 is not larger than 4. So we would just have 5 and 6. So these are really nitpicky sometimes. So make sure to double read stuff and that it makes sense. Okay. They put this all sorts of out of order, but we're gonna change the order a little bit. So theoretic, classical, probability. That's the probability we've been dealing with so far. This is we know how many ways we can roll a 6. So what's the likelihood of this thing happening based on just the theory of it? If we were to actually run some of these experiments, we might get different outcomes just because the world doesn't work perfect like we want it to. So for our theoretic probability, I'm skipping around here. We have the probability that some event happens is the number of ways that event can happen over the total number in our sample space. So count them up, divide. You can present your probability as a decimal, a fraction, or a percent. Don't do percents. Decimal or fraction is typical. You get into percents, that's a little bit, I mean, it's really the same thing, but looks weird. So for me, I wouldn't care if you gave me either one or if you gave me an unreduced fraction. Homework is going to care. So look at what they tell you and round where they tell you to round. There's always little blue writing in parentheses near the entry box somewhere that will tell you where they want you to round. Pay attention to that. So let us roll 2 die. I do not have a good picture of this because I didn't write down what page number this is on. There is a nice picture of this in the notes or in the PowerPoints. So if we roll 2 dice, we're going to sum up the rolls. So let's say I have a black and a pink. Those are the colors I have here. And my very ugly dice. So the first one, on the black die, I roll a 3, and my pink die, I roll a 5. That gives me a sum of 8. Now that is a different outcome than rolling a 3 on the pink die and a 5 on the black die. So this sum is also 8. So it's important to remember that there's often 2 ways we can have the same outcome. So for us, a 3, 5 is not the same as a 5, 3. Because think of your dice as different colors. 3 versus 5 on the black die matters. So based on that, how many numbers are in our sample space? How many outcomes can we have? Well, we have an answer? How many? You said 2? More than 2. If we roll 2, how many like potential outcomes for the different die? Well, the first die we can roll a 1 through 6, right? The second die we can also roll a 1 through 6. So in this case, we're going to multiply. So 6 times 6 gives us 36 possible outcomes. So I'll list a few. We could have 1, 1, 1, 2, 2, 1, 5, 6, 6, 5, 6, 6. So there's 6 ways to choose the first thing and 6 ways to choose the second thing. Gives us a total of 36 possible combinations. You look up a dice chart, it helps. Okay, so let's look at a couple events. Event 1 is a sum of 7. Event 2 Event 3 will be a sum greater than 12. So again, we're getting nitpicky here with these. It might help to write some of these out, especially early days for these. So we have 2 die. How many different ways can we make a 7? Well, 1 plus 6 equals 7. We can also go the other way. 2 plus 5. And again, the other way. And then 3 plus 4. Way. But after that, I would be 4 plus 3, which is already listed there. So we've covered all of our possible ways to make a 7. So how many is that? There's 6 of them. So the probability of event 1, 6 out of 36. And I can reduce this to 1/6 if I prefer. Or I can turn it into a fraction if I prefer that too. Doesn't really matter. It's up to you. Okay. How many ways can we make a sum of 2? Well, the smallest thing I can roll on either die is a 1. So there's really only one way we can make it 2. They both roll a 1. So this is going to give us probability of event 2 is 1 out of 36. Finally, greater than 12. And this is again where we have to be picky. Can we roll anything greater than 12? No, the biggest thing we can roll is a 12 because we have a 6 and a 6. So there are 0 ways. Ooh, that looks like a 6. Try again, 0 out of 36, which is 0. This one would be called an impossible event. So if our probability is 0, it's impossible. It cannot happen. If our probability is really small, it's still possible. It's just, unlikely. If the probability of some event equals 1, this is a sure event. That means this thing will happen. So for the example above, if we roll a sum of 1 through 12, well, that's going to happen because those are all of our possible outcomes. We know that's the thing. So that kind of gives us another rule of probability we're looking at. So a sure event, we know what happens is a probability of 1. An impossible event is a probability of 0. Can we have probabilities that are greater than 1 or less than 0? Less than 0 would make it negative, which that doesn't make sense. We can't have more outcomes than we have in the sample space. So for any event, zero less than or equal probability of E less than or equal 1. So our probability is always between 0 and 1. Can't be less, can't be more. Suppose our sample space has a whole bunch of things in it. We don't know how many. So event or thing 1, E1, E2, all the way to En. If we want to take the probability of each event and add them up, what do we get? That's not 3, that should be an N. So if we add up the probability of every possible outcome, as long as they don't overlap, that should give us a 1. And we're going to see that with our next example. So we'll see how that works. In 2 examples, sorry. This brings up empirical probability. This is a probability based on observation. Or we can think of it as survey data. So we don't do anything, it's not an experiment, we're just seeing what happens in some sort of event. So let's say we have a bag of Skittles because they're tasty. And in this bag, we have 182 Skittles. I don't know if that's a typical bag size or not. I haven't really counted, but I just stole numbers from the book. It's fine. So we have 182 pieces of candy. 24 of these are red because red is my favorite Skittle. What is the probability that a random Skittle we choose is red? So this is our survey data. We've taken a bag of Skittles, counted how many pieces there are, and counted the number of red Skittles. So we don't have to share those with our friend. So if we mix up the bag, reach in and grab one, what's the probability that what we grab is red? Well, let's say probability of R. I always start with the denominator. How many Skittles do we have? 182. And how many of them are red? 24. So our probability is approximately 0.132. So, what, 5 colors in there? That seems like a little light for the reds. There should be about 20%. It's a sad bag for me. If you don't like red, that's a happy bag for you. Okay. What's the probability a Skittle we choose is not red? There are 2 different ways we can think of this, which is really the same way, just stated 2 different methods. So of our bag of 182 Skittles, how many of them aren't red? Yeah, I'm gonna get my calculator out so I don't look foolish when I subtract. I have 182 24 of them are red. So we have 158 Skittles that are not red. So 158 out of 182. Gives me 0.868. What do you notice about those two numbers? I have 0.868 and 0.132. What do I get if I add them together? Hopefully we get 1. So the probability a Skittle in our bag is either red or not red is 1, because that's all of our Skittles. They're either red or not red. Pretty straightforward on that. So this tells us another way we can figure out the probability something is not. So probability of red complement, or not red, is 1 minus the probability of red. So sometimes the forward way is easier, sometimes the backward way is easier. It just depends on the problem. But this is helpful. Sometimes it's easier to figure out how something doesn't happen. So that's kind of our example of the thing I said was coming. Probability something happens, probability something doesn't happen, should be 1. All right, our last empirical example is going to take me a sec to write up. So how do we get to work? This is a survey because it's just, we ask people. Okay, so we have our different methods of getting to work. And we took a survey and we find that 153 people drive on their own. Actually, I'm gonna need too much black, it's killing my eyes. 153. 22 ride with a friend or carpool. We have 10 that take public transportation. 5 walk. 3 have some other method of getting there. I'm guessing they fly, I don't know. And 7 of these lucky people get to work from home. This is a total of 200 people. So if we want to figure out the probability that anyone is in any of these particular categories, we take our frequency divided by our 200. And we're going to turn that into a decimal because it looks nicer in this case. If they're nice fractions, we'll leave them, but that's not a nice fraction. So 153 divided by 200 will give us 0.765. 22 divided by 200 is 0.11. I'm just going to fill them in. And if we add all of these probabilities up, we should get a 1, which that seems reasonable in this case, provided I didn't write something wrong. I think I'm okay. So for empirical, we just take the number in each category, divide by the total number. Excuse me, that's our probability. The last thing for chapter 5, and then I'll see how we're doing. Is we simulate probability experiments. Basically, we have a computer program say, hey, run this probability thing a bunch of times and tell me the outcomes. Anymore, we can have ChatGPT do that. I had a homework assignment where I needed to run probabilities, needed some random. So I told it to do that because it's boring and why not have them do that? You can have StatCrunch do it as well. So slide 157 is the one that'll give you the StatCrunch steps. So I'll leave that to you. But this is a nice way of, if you have some idea of an experiment and you don't want to sit there and flip your coin 2,000 times, you can have a computer do it for you, plug in the randomness, the probability of each thing, and see what happens. So it's a good way of running an experiment without running an experiment. So yeah, that's an interesting bit. I am going to leave it there. Sadly, we don't get to do my favorite parts of probability where we count different things. One time I had us figure out the probability of winning Powerball of any amount, and that took me 2 class periods, so I never did it again. It's a very long process to talk through, but it's interesting. So, all right, that leaves us in a good spot here. We've caught up. Next time we'll go over chapter 7. And then we'll be in good shape. This, we'll just